I'm here with my team Divyansh and Suman to present the paper Learning to Cache with No Regrets. So, before we actually get to the details of the paper, we need to understand what is caching, why should we do it, and how to cache, right? So, caching is nothing but a high-speed data storage layer. It stores a subset of data that can be accessed by the user. This data is generally the most popular data that any provider has. Why should we do it? Because it speeds up the performance and improves the user experience since it reduces the network lag for a particular request. So that's why a lot of companies such as Facebook, Google, Apple, Oracle, YouTube, Netflix are investing good amount of research and to cache in a better way. And how to cache? There are a lot of techniques, and we need to choose a technique that best suits us. So, and we'll get into more details later. So it's not an easy problem to solve because if our algorithm is a poor caching algorithm, it will actually degrade the performance rather than making it better. The problem of finding an optimal online caching algorithm has been open for decades. And ideally, what we're aiming for is to design an online caching policy with high hit rates so that we can find most of the data in our cache or the most popular data in our cache. Next. So, what are some open questions that we have? So, some open questions that we have is how can we make use of a smaller storage nearer to the user? And since it can just hold, the cache can just hold a subset of the file library, what should we store in our cache? And how should we maximize this performance? So, similarly, if we are going to say it more poetically, it can be said, we can say, should we cache or not? So, yeah, now we'll move on to some intuitive caching policies. So, yes. One of the most, common and intuitive policy is the least recently used caching policy. So the idea is very simple. You have a cache. You're gonna cache the items that have been seen most recently, and you're gonna evict the items that were seen much previously. So in this case, we can see that we see that eventually 8 gets popped when 3 was requested. Another intuitive policy is also called the least frequently used policy, which essentially when an element is cached, we maintain and store the number of times that element was read. So in this case, initially A, B, C, D, and these are the number of times each element was read. Now, since we have got a new element F that needs to be accessed and our cache doesn't have it, so we're going to remove the element that was least frequently read while in the cache. So E is eliminated. But as we can see, these are intuitive policies, but they have their own challenges. So LRU works very well and has a very high hit ratio. So by hit ratio meaning that you're able to find the file in the cache. The number of times you find the file in the cache upon the total number of total number of requests. So LRU does very well when you need to find files in a certain locality, a small number of files. That's where it really excels. LFU has the highest hit ratio for a constant request distribution. So by that I mean that, hey, let's say file A is always the most popular, file B is the second most popular, so file C is the third most popular, and this request distribution is gonna stay constant throughout. So another thing that we can see here is that the policy that we need to choose depends on the request model. So, and the request model can be changing over time. I mean, a movie that's famous today is not going to be famous tomorrow, and so many things we can think of, right? So now the paper introduces a mathematical loss or an evaluation metric apart just from the caching ratio. It's called as a regret. The reason they do this is they want to compare any given policy with the offline policy. What's an offline policy? Let's say there's a policy that knows the entire request distribution, when it's gonna change, what element's gonna come next. So that is ideally the hypothetical best any caching policy can achieve to be, right? So regret gives a more a better way to choose good caching policies from bad ones, because let's say the request model changes over time, the regret would also reflect that, right? So you're going to have higher regret when you are having more cache, you're not finding elements in your cache, and lower regret when you're finding elements in your cache. So yeah, next, let's just think of the regret of the existing policies. So the regret of existing policies is actually poor, because as we just demonstrated above in the few slides ago, that not every caching policy, such as LRU and LFU, can work for each request model. They have their pros and cons, right? So they only perform well under certain situations, and they have a poor regret, which is in the average time bounded by T. T here is the number of times you're requesting an element. So that's the average. And if you a simple example to show where LRU is not so good is, let's say you have been given elements in such order, and now when the C plus 1th element or file would be requested, LRU will evict the first element, but the best policy would have evicted element C, and that would have ensured a cache hit of element 1 when it would have been requested again. But if you see, this is how the regret piles up, and this is why regret is a very practical metric to refer to, right? Now, so what's a goal? A goal is to somehow design a universal caching policy that can learn to adapt to any changing request models without any prior knowledge, right? And in doing so, we would also like strong performance guarantees, which can be done by doing some regret analysis, so that we know that our caching policy really does work, right? And the intuition is, can we somehow learn from the past requests and try to predict the future ones? Similarly, at the same time, can we cache and evict files based on a file's likelihood of being requested in the future, essentially? So if that's in hindsight, that's how the offline algorithm also works, right? So can we somehow get closer to the offline algorithm? Now, the system, let's quickly go over the system model. So in our system model, we have a library of n files and a cache size of C, where C is lesser than n. So if there is a cache hit, the reward or utility is given by W, right? Only one file can be requested per request. So you can just request a file in one request. Y is defined as the fraction of each file stored within a cache. So in short, we do allow a file to be stored in percentages, like something like 40% of the file is stored in a cache, 50% of a file is stored in a cache, or some other file is stored 20% in the cache. So that's something we allow in our system model. The only constraint is that the total sum of the storage of different cache files has to be lesser than or equal to the cache capacity. So for example, let's say we have 5 files and we have stored 20% of each file. So 20% of each file has been cached, and the total capacity of this cache is one complete file. So this constraint is satisfied by this example. Now, as I said earlier, we would like to strive towards a universal policy which can learn to cache inevitably from its own mistakes, right? So this will evolve the caching policy to make better decisions, right? And in doing so, if we have a regret lower bound, so by the lower bound, what we mean is, so it's a result where, let's say, any universal policy will have at least this much regret, right? So if we have that kind of a result, we can understand what policy is good, what universal policy is good, should we use it, and what's the regret we have been getting so far, right? So how can we minimize our regret and at the same time maximize our cache hit rate, right? So doing so will give us a powerful algorithm. And while talking, the paper does give a very comprehensive proof of the lower bound, but a more practical result is that the regret of any online caching algorithm is theta of root c into t, where c is the cache size, which is lesser than the total n by 2, where n is the number of files. So basically lesser than the 50% of the total files you have, and t is again the time horizon, right? So eventually how many times we are going to request and the time that goes with it. So they essentially, what they're doing is they say that when we want to maximize the cache hit rate, essentially try to find each and every file which is popular in the cache, the average regret for such caching algorithm can be given by theta of root ct. Now moving ahead, so the algorithm proposed in the paper is online gradient ascent caching policy, and they refer to it as OGA. The idea of this big big name is very simple. How can we cache files based on file popularity? File popularity changes over time. So the algorithm refers to this as gradient, and based on the gradient we make our decisions, right? So, and this caching policy has the regret equal to the lower bound that we just discussed earlier. Now, so this, I'm pretty sure this is the algorithm, but it's super scary just to looking at it, right? But intuitively, if you're just supposed to look at it, it's given by this is the gradient part, and this is at any time t, what's the cache configuration, and how it's going to change for time t plus 1. But it's scary, I know. Let's try to look at an example, a simple example, and try to see how the algorithm works. So and let's say in our example, at time t for a server, we have 5 files and a cache with the maximum capacity of 2 complete files. So what I mean by this is, at max you can just store 2 complete files in a cache, but since we are allowing partial caching, you can store up to 2 max, basically up to 2 complete files. So initially file 0 and 1 are stored, right? And the utility and reward for storing all files is w equal to 1. So essentially for each file you have a utility of let's say w equal to 1. So basically that's the reward, right? So if you're able to find the file in the cache, the reward is w equal to 1, right? Now at time t plus 1, let's say we receive a request for file 2. So file 2, this is how the request would look like. We have received a request for file number 2, and now our initial cache configuration was 11000, but how OGA changes the cache config is, it's gonna penalize the files that are file percentages that are greater than 0. So in this case 1 and 1, and for the file that has been requested, we are gonna take a step in that direction, and at the same time what we're gonna do, we're gonna increase its file allotment in our cache. So basically penalize the files that are already present in our cache and increase the allotment of the file that has been requested. So this is how it's gonna change. And finally, so as we said previously, the step size is basically a hyperparameter. And for our case, it's given, for our example, we're going to assume it to be 1. So we're going to calculate the gradient. The gradient is actually given by as w into x. So, and now we regularize these values. So essentially now we're going to increase the allocation for the requested file and reduce for the pre-cache files. So in this toy example, at t plus 1, our cache configuration is going to look like 0.5, 0.5 and 1. So what does this mean? That we now store 50% of file 0, we now store 50% of file 1, and we store 100% of file 2. So this is how the cache has got updated. This is entirely this is how the algorithm basically works. Now let's try and find some similarities with LFU and LRU. So like the least frequently used algorithm, highest frequencies influence cache, but they're regularized. So by regularized meaning that, so let's say in LFU, when you have a file that has been that's already present in the cache, so we're going to increase its frequency, but we do not change anything else, any frequency of the other files, right? But here by regularization, that we kind of say that, hey, now I'm going to increase the allotment here, but I'm going to decrease the allotment for others. So it kind of adapts that, and that actually sort of represents the probability of finding the file again. So that's what I meant by regularization. Now when neta equal to 1 and w is 1 for all files, it's gonna be similar to LRU. So in our example, we had this condition where neta was 1 and w was 1 as well. So what did that mean? We were actually on the most recent request, we were making our decisions, but LRU will remove the entire file. OGA removes them gradually. So it gives OGA room to optimize and not have a higher regret, right? So that's how it's similar to both LFU and LRU. Now moving ahead, so the simulations in the paper, they simulate for different request models, but in each request model they have total files as 10,000 and a cache limit of 3,000. So they simulate for the use case where we are modeling a CDN cache, right? So how can that be modeled? And let's say YouTube request caching. So there's a lot of work being done behind the scenes to how can we cache videos and what percentage of caching these videos. So as very initially we did mention that each policy has their strengths and weaknesses. So that's true for LFU and LRU as well. So OGA is able to mimic the performance best amongst LFU and LRU. So by that what I mean is, so for a certain request model, probably least frequently used is the best way to go. So OGA would mimic that, and in the other request model, it would be better or mimic the performance of LRU. So in our simulations, we see that in the case of CDN aggregation, it mimics the performance very closely of LFU and has a big gap between LRU and our policy. And similarly, for the YouTube video simulation, the results show that it's much better than the LRU algorithm, LRU policy, and it's LRU policy. The hit ratio is much better than that, which is the second best in this case. Now coming to network caching. So in network caching, the previous example that we had was just for one single cache. Network caching is when we have a complex network of caches and servers and users. So there's a lot of things that now get introduced into the picture. And so this network of caches is actually represented by a weighted graph. So if you think of it, the edges weight can be delay, can be distance, can be bandwidth, can be so many things that actually determine the quality of service. So in our case, let's say we have two users in College Station, and one user is connected to the cache in College Station, and one user is connected to the cache in Austin, and the other user is connected to Las Vegas as well. We would want to maximize the cache hits at places which is closest to the user. So that would give the most seamless experience. So yeah, and the utility. So the utility, if we recall, was the reward that we get once you have found a file in your cache. That also depends on the network configuration, because depending on the network and the parameters that go into it, like in this case distance, essentially, that actually influences the utility that we get. You don't want a user to hit a cache which is very far away, right? So yeah. Now more formally, bipartite online caching is a special case of network caching, and this is the more formal representation of the example above. So a request cannot be routed from an unreachable cache, and a cache cannot serve more data than its capacity essentially, right? So now moving forward, so the authors extend OGA and propose BSGA, which is the bipartite subgradient algorithm. They extend OGA to the bipartite caching network problem essentially. And the catch here is that in this domain, the gradient can't be calculated everywhere. So the gradient in our OGA was the multiplication of the utility into the request for at each file location. But since it's not possible to calculate gradient everywhere, and the more theoretical answer would be that this function domain is actually concave in nature, and that's why gradient calculation is not always possible. They calculate subgradient, which is an approximation of the gradient in OGA, and the subgradient is proportional to the increase in utility obtained from increasing the file location at a particular cache location. So allocation at a particular cache location. So I know this is kind of obscure, but essentially what it means is if you're going to increase the utility if you're going to increase the file allocation at a particular cache, what's the increase in utility obtained? What's the increase in sort of rewards? A more reinforcement learning parallel would be what's the increase in reward obtained? So, and how does this algorithm work? Each cache runs OGA locally, and the decision is made where to fetch data from for a particular user. So that's essentially the gist of the algorithm. And in this simulation, they have a setup of 3 caches, each with a capacity of 10 and 4 users. So they have varying utility for each cache. So maybe in our toy example, as we just had, let's say if a cache in Nevada should have less utility compared to a cache in College Station if the probably if when the user is in Texas, right? So that's the same concept here. There are 100 files in total, and eventually popular files start appearing at the high utility cache, right? And the BSA algorithm beats the second best algorithm, lazy LRU, by a big margin of 45.8%, and the metric used here is average utility of different caching policies. So what that means that let's say the utility can be thought of as rewards obtained over time, and average utility is basically the total rewards upon the total time essentially. Now let's quickly go into the limitations. So one limitation which is actually directly coming from the system model is the fact that the algorithm can only process one request at a time, right? Which is, I mean, that's maybe not ideal always. And the algorithm is also hyperparameter dependent. This means that you need to do tuning to find the best parameter for running the algorithm. So in this case, in the graph on the right side, we see that the hit ratio increases as we decrease the step size. And another thing we can see from this graph is that the algorithm takes a good chunk of requests to converge. So this is in the order of 10 raised to 5, and that means that there's a good amount of time you will require for the algorithm to become to become accurate and high performant. Some more limitations is that the algorithm assumes that we can store very small fractions of files. That's not ideal in every case, right? And for the bipartite network caching problem, OGA has to be done again and again at each cache. So that makes it expensive and time consuming when there's a more complex setup with multiple users, multiple caches. So it can get expensive computationally. So what does it relate to in class? I mean, network caching draws some parallels with P2P systems because both systems try to optimize the quality of service by improving the network performance, and many of times the systems are actually used together. Future scope. So instead of having infinitesimal portions, we could have discrete chunks of files that's actually that proposal increases the performance in cases when the files are particularly large. And so for network caching, unlike what we showed for OGA, when the authors do not provide any lower bound or regret analysis for the case where we run it on the network caching problem. I mean, work can be done to give a tight universal lower bound, so that gives a more theoretical analysis into the algorithm that has been proposed. So which would be a significant contribution, right? So conclusion, we compare existing policies such as LRU, LFU to OGA. We propose OGA, and it's a universal caching policy, which again means that a caching policy that evolves over time and starts to learn. It's simple and doesn't require knowledge of request models, and OGA can be extended to the bipartite caching networks domain, where routing is also considered while making decisions of which file needs to be cached where. So some more references that we, in case for additional reading for anyone. And yeah, thank you. I hope you have a great day.